everybody again. I'm very excited to start the first session. As Stefania said, we will have two talks in this session. The first one is by Marumi Kado, and then John Ellis will follow. So let me make a very short introduction to Marumi. So Marumi is a professor at Sapienza University of Rome since 2016. He's a member of the ATLAS collaboration since 2003. He's currently deputy spokesperson of ATLAS for the period 2021 and 2023. And he was previously Higgs convener for ATLAS since 2012, from 2012 until 2014, and then physics coordinator from 2014 to 2016. So these, as you can see, are really the dates, the years in which the Higgs boson was discovered and the main physics analysis was realized. And in fact, this is not a chance. It's not a chance that Marumi was first Higgs convener and physics coordinator during those years, because he was certainly one of the main, most important characters in the Higgs discovery. And he gave important contributions in the analysis in all decay modes of the Higgs boson, especially in gamma-gamma and Higgs-2,4 leptons. And he also made a very important contribution in the statistical analysis. So at this point, I'm very glad to give the stage to Marumi. His talk will be on the discovery of the Higgs boson, which is a 30-year-long experimental enterprise. Please, Marumi.
So thank you very much, Stefania, and thank you very much, Roberto, for the very nice introduction.
Sorry, Marumi, if I interrupt you immediately. I forgot to say that during the talk, we will not have questions, so questions are devoted to right after the talk. If there is any urgent question or comment, people can write in the chat, okay? So after the talk, we will have 10 minutes for discussion and questions, and then at the end of all the talks, we will have a discussion where we can have talks and we can have questions for any speaker. Please.
So yeah, again, thank you very much, Roberto, for the nice introduction. I just have to tell you, I was mostly on the Higgs gamma-gamma at the start and during the discovery. I did not work directly on the Higgs-2,4 leptons, just to make sure this is clear. Also, I mean, I really want to stress how collective, of course, this work is, and it's essentially impossible to distinguish easily a person contributing more or less to this incredible discovery, of course, and it has been a collaborative result, and I try to show this to you also today. I'm incredibly happy and honored to be here and celebrate with you the 10th anniversary of the Higgs discovery. And Roberto gave me the very hard task to cover a huge number of subjects, so I'll try to go through them, and I hope I'll do justice to what he wanted to see. So, and here you have a beautiful event of a 4-lepton, in fact, in the ATLAS detector. And let me start by saying that this week was an incredibly packed week. So just yesterday, we started again run 3 successfully at 13.6 TeV. Maybe some of you have followed on YouTube the event, so you can see pictures from the control room. Everything went fine. And if you haven't followed, you can see some news at the links that are pasted below. It was also a packed week, as you might have seen, on the 4th of July, which was the specific date of the discovery. We had 2 papers released for that occasion on Nature by ATLAS and CMS, summarizing and having original combinations of the couplings of the Higgs boson just for this event. And there is a large series of papers and a complete Nature portfolio published for the occasion. So please go and visit this website. It's going to tell you a lot about the Higgs, and there are very nice interviews there as well. And then here's the outline of my talk. I will first go through a quick preamble, talk about the machine, talk about the expectation, and how I will try to convince you we went well beyond the expectation. I will tell you a little bit about the Higgs discovery, and then discuss the status of Higgs physics, briefly mention the essential role of theory predictions, and then discuss early evidences for rare processes, and want to finish with how we think we can make the impossible possible with Higgs physics at the LHC. Important references, a lot of in particular historical, I will not dwell too much on the history, but has been taken from two symposiums. The first one was the last year on the 50th anniversary of Hadron Colliders at CERN, and on, of course, the symposium of Monday, where there were absolutely beautiful talks. So, I mean, a lot of the details that what I would just be brushing here, you can find there, of course. So let me start immediately with a preamble. And it's about 4 decades of Higgs searches before we started the LHC. And you will see that it's often mentioned that we had no ideas of what the mass of the Higgs boson should be, except, of course, for the unitarity of the vector boson scattering and triviality arguments. Now, there has been a host of searches before the start of the LHC, starting in the early 70s with transitions in atomic transition of oxygen-16 or polonium-214, the famous O+, O+ transition, mesons decays, kaons, and pions, but also muonic at atom transitions, where there was a discrepancy that was observed and that raised a lot of interest at the time, and then was excluded by data from neutron nucleus scattering. There was also data from pion-proton and photon-proton scattering, and other arguments such as cosmological constant consideration, which was the precursor of the cosmological constant problem of the Higgs potential, and also observation of the microwave background also inferred interesting limits on the Higgs. But of course, the systematic search of the Higgs started really with the proton-proton collision and E+ E- collision. And here I just mentioned the several machines that were involved in this, and this is throughout from the 70s all the way to today, of course. And then I just wanted to mention two very important references. One, I'm sure will be mentioned by John, probably both in his talk. I mean, the first one is the phenomenological profile of the Higgs boson, and where really a lot of the phenomenology of everything that has been done in those 40 years of Higgs searches has been laid down, and of course the Higgs Hunter's Guide, which was a fundamental reference. Now, I'm just highlighting the two machines, the proton-proton collider, the proton-antiproton collider Tevatron, and the LEP machine, which went up to an energy of 209 GeV, because this is what brushed the picture of where we stood in Higgs searches prior to the start of the LHC. And so the LEP provided the absolute lower and unabsolute lower limit on the standard model Higgs in E+ E- collision, mostly through the Higgs triangle process, where the Higgs produce an association with the vector boson. And this limit was 114.4 GeV. Okay, and the Tevatron had a very good sensitivity around the mass here, as you can see, of 160 GeV. So I will correct this, of course, in a minute after the talk. And what you can see here, this is the likelihood, including electroweak precision, and it shows you what the likelihood of the Higgs boson was prior to starting the LHC, essentially. And of course, this meant that the low mass region here between about 115 and 160 GeV was extremely interesting, and of course, a lot of the attention was brought to that region. So I'll come back to this. And really these 30 to 40 years of searches was culminating, I mean, the attention was culminating in 2008 before we started taking data. Also, I highlighted here the Tevatron because you can see that this high level of likelihood here means that actually Tevatron analyses were very sensitive in this region, and maybe some of you might remember that was the time where we started the LHC, and Tevatron was still taking data, and we were in competition at that point. And if the Higgs had a mass of 160 GeV, the story might have been very different than what it is today. And of course, there was the no-lose theorem. So from this preamble, I would like to talk about the marvel of technology that is the LHC. And all of you have seen this picture of the LHC, which is hosted in a 27-kilometer tunnel, which was the LEP tunnel, the LEP collider tunnel, which is at an average of 100 meters under the beautiful region of Geneva, with the lowest point at 175 meters. So let me just give you a brief history of the LHC, and it's very interesting to see the time span from the first ideas to where we are now, also to inspire us and project ourselves in what could come next for future projects. So the first mention of the LHC was in 1977 by Sir John Adams, the former CERN director, as an option of a superconducting hadron collider to be hosted in the lab tunnel. And this was just mentions. But really, when it all started was at the ECFA workshop in Lausanne in 1984, and this is the words of Peter Jenny. And here is a very, very short timeline, just to try to give you the essential dates to see what happened from 1984 to up to today. So from 1984 to 88, there was this very important CERN ECFA workshop, and the lab tunnel was completed. So of course, these are two very important aspects. So lab was starting, and at the same time, we were preparing for what could come next in the lab tunnel. In the 1990 started, 1990 and 1992, there was a very important workshop in Aachen, and this you will see is where the definition of the main discovery chains was made. And also in 1992, when ATLAS and CMS letters of intent were written and submitted. Also in 1993, then in 1994, there was a very important event. I would not discuss this too much. I mean, it happened before I started physics, so I will leave people having really leave this period to comment more in detail. But there was the cancellation of the SSC. This was a very important event. At the same time, there was the first prototype mainnet for the LHC that reached a magnetic field of 8.73 Tesla stably. And this was, of course, a very important milestone. And all of these led to the approval of the LHC in 1994. Then in 1997, 98 was the approval of the ATLAS CMS LHCb analysis experiments. And then started the construction of the experiment, and that lasted approximately 10 years. So from 2003 with the cavern, which were completed and installation could start, up to the completion of the installation of all the LHC dipoles. And of course, this hasn't been a simple route to install the whole machine. You can see a very nice talk by Lynn Evans at the symposium on Monday. I was retracing this history. So after having been stocked in parking lots for a long time due to issues with cryoline, they were all individually checked at SM18 and installed in the LHC. So the 10th of September in 2008 was the official start of the LHC. And after a hiatus of a year that I will discuss also later, really since 2009, we had 12 very successful, actually 13 successful year of operations and landmark results. Now, immediately after, in 2010, the HL-LHC design study was submitted, and you can see here now the latest schedule of the HL-LHC project, which spans from 2010 up to 2040 and beyond. This remains to be, of course, decided. And it was 2016. So this is just to mention that we always try to think a step ahead. And to complete this program, of course, there are major machine and detector upgrades that have already started, and a large part of this Longshot Dime 2, where we just ended yesterday officially. There was a very intense preparation for the high luminosity phase, and of course, another long shutdown is going to be needed in 2026 to get there. Now, the LHC is often referred to as the most ambitious scientific experiment in history. And this is a quote by John Giuditti in the Zepso Space Odyssey, a very nice book about the LHC. It is an arrival at the energy frontier, and it is outstanding at the intensity frontier. It has been surpassed only by Super-Clec B in 2020, not by much. So just to illustrate why this is a gigantic project, I just want to give you a few numbers beside the circumference. There are almost 10,000 magnets constituting the whole machine, with 1,200 bending dipoles that have to reach 8.3 Tesla, with currents at over 11,000 amps. And the beams are made of almost 3,000 bunches containing approximately 100 billion protons each. And each bunch is separated by about 7 meters. So just to give you an idea, that just the beam has an energy, an energy of 350 megajoules, which is equivalent of a train like a TGV running at 150 kilometers per hour. Now, the construction and commissioning of the LHC, I'm just showing a few pictures. Here you see at the SMX-18 where all the dipoles were tested, and then one by one were lowered into the tunnel and installed. And just to show you what it meant to actually operate a beam of 350 megajoules, you can see in the picture here a groove that has been made by the beam just coming near the screen on the beam screen inside the vacuum beam pipes. And this 350 megajoules is only the beam. If you just take into account the total stored energy in the magnets from the 11,000 amps current, it's about 11 gigajoules. And this is enough to melt 15 tons of copper. So this is also very important to keep in mind. So the operation of the LHC has really propulsed the machine community into a new realm where it was extremely important. The operation is not only important to get performance, but also just to make sure that no damage is done to the machine. On the side of the experiment, I'm showing 2 slides shown by Peter Jenny at the symposium, which are really very nice and showing the vision of the founders of the experiments and how general purpose detectors were well thought of well in advance. So the concept was really thought of in the early 80s. And here I just wanted to show you what are the physics cases and all the signatures that were tried to be considered. So they span all the standard model cases, Higgs cases, but also supersymmetry. So supersymmetry was of great help to us actually to make sure that the detectors would cover a huge dynamic range in their performance. And this was, of course, extremely important and has turned out to be a great help for us to reach outstanding performance nowadays. And there was 15 years of intense thoughts put into the design. I'm just showing nice drawings that were shown also at the symposium on Monday. And here are the 2 detectors. So these are the designs. So this is how the design has turned out to be with our 2 big general purpose detectors. ATLAS, which is 25 meters per 44 meters length, weighs over 7,000 tons and has over 100 million readout channels. CMS is 15 meters in diameter, 21 meters in length, and weighs 14 tons with 75 million readout channels. You have a drawing there. Now I'm just flashing to you the main characteristics of the 2 detectors. I'm just going to say just a few words for you to keep in mind that one of the main differences between the 2 detectors is how the central solenoidal field that is used to bend the tracks in the inner detector is, I mean, for ATLAS, it's 2 Tesla, for CMS, it's 4 Tesla. And this actually makes a difference in certain kinematic ranges. And for instance, also the superconducting coil is outside and englobes in CMS both the electromagnetic and the hadronic calorimeter. So this actually makes a difference in design. You will see it in difference in the resolutions in how we measure photons, electrons, but also muons, as in ATLAS. There is a complex spectrometers for muons on the outside. So just this to flash some of the difference between ATLAS and CMS, and you can look at this slide in more detail. Now then, there's been 10 years of construction that I will just brush through very rapidly, showing to you a few pictures. So here you have, again, ATLAS on the left and during the installation, and CMS on the right. And here a few pictures of several subdetectors. Actually, there's one that's not from the initial installation. One is just from the upgrade of Photorun 3, and I'd like to try to understand which one it is. Now, I just wanted to also come back to one interesting and important quote, which was made by Chris Llewellyn-Smith, who was CERN Director General from 1994 to 1998. And this was said at the 50 years Hadron Collider Symposium at CERN last year. And what it takes, it was a reflection about what it takes to have a machine approved and what took the LHC to be approved. So a robust scientific case, and large with an exploration of large new domain with good reasons to expect discovery. Of course, this we had in the nodos there, and this was extremely important. Uniqueness, I hope that I've showed you by just the few numbers that I flashed before that this was quite a unique machine from many aspects, from the energy frontier to the intensity frontier to how complex such machine is. A unanimous support of the world particle physics community. So I wasn't there at the time, but I suppose it was there, in particular after the SSC was stopped. And a general technical success of CERN, I think that there's no question that was there, and no budget bumped, which was an imposed condition. So I think all the conditions converged for the approval of the LHC in 1994. And I also want to stress the breadth and the diversity of the scientific program of the LHC, not only in Higgs physics, but well beyond. And in fact, the design, the general purpose design and the exceptional operation of the LHC really brought an incredible diversity in the physics program of the LHC. Okay, so that brings me to my third section about the performing, about how I think the machine experiments and in general the entire community has performed well beyond expectations. So first, the start of the LHC was not exactly as we expected it. You might remember in 2008, there was the thought of the end of the world during 9 days, or at the start of the LHC. This, of course, did not happen. The world survived the Big Bang. However, that was not the end of the world, but we had an incident at an interconnection between two superconducting magnets, and about 700 meters of damaged area occurred, with 39 dipoles and 14 quadrupoles that were deteriorated and had to be replaced. The incident also implied the beam vacuum, that the beam vacuum was affected over almost 3 kilometers. It took 1 year of repair. The whole of LS1 to the long shutdown, the first long shutdown, to consolidate the interconnections. But then we can start and take data very successfully. And just to show you this, you can see here the integrated luminosities as a function of time for each of the years, each of the periods of year. And of course, the last year was the most successful one, where we collected about 16 femtobarns per experiment. Collecting this data so fast meant that we have a lot of interactions per bunch crossings. We reached about 30 at run 2, but also at run 1. And we had an integrated luminosity at run 1 that reached 20 inverse femtobarns. So 20 inverse femtobarns, and 114 inverse femtobarns at run 2. At run 1, we were at the center of mass energy of 7, 8 TeV, and run 2, we went up to 13 TeV. Now, however impressive 16 inverse femtobarns of data per year could seem, to reach the goal of the HL-LHC of over 3 inverse attobarns would require 50 full years of running the LHC. So of course something had to be done, and this is the whole the entire program of the upgrades that I discussed previously. Now I just wanted to flash to you what the nominal parameters of the machine were, and what they have been at run 1 and run 2. And you can see that in essentially most of the possible machine parameters, the performance has been surpassed, except in the center of mass energy. We're getting close now at 13.6 TeV to the 14 TeV nominal energy, and in the number of bunches that also we're getting close to what we were. And also I'm putting here the beam parameter that I expected for the HL-LHC. So it is clear that LHC has performed well beyond expectation, and we reached nominal performance very, very fast. Now, of course, reaching this performance also implied that we have to deal with huge challenges in trigger, data acquisition, and software. And first of all, the trigger challenges, we have to select 400 to 1,000 out of 20 million events per second, while keeping all the interesting ones, including for unknown interesting new physics. We have to read out and reconstruct those 100 million channels I discussed previously at a rate of almost 2 kilohertz, and the raw event size about 1.5 megabytes per event. It's a huge computing challenge to reconstruct, store, and distribute all these events, and the entire grid, but the entire CERN computing system covers over 750 petabytes of disk, and 1,200 petabytes of tape, but also the entire computing grid that has to be managed by WSCG. Comprises of about 1 million cores. So you see that this is really a macroscopic scale computing challenge for CERN and the experiments. It's an analysis challenge, of course, because we have to maintain as much as possible very high reconstruction and identification efficiency, and while rejecting fake objects and doing this at a high pileup. And this is, of course, an ideal environment for deep learning. And this I will try to show you how this has been developed. Now, the computing grid and the computing resources management has performed really well beyond expectation. And this is proved just by the fact that all the data that was taken could be analyzed and successfully. Now, just to flash you some of the performance achievements. First, in terms of trigger, run 1 and run 2 was extremely successful, in particular, because we didn't have to increase the levels of the thresholds, despite the increased level of pileup. And this, in fact, is something that we have been able to maintain throughout run 1 and run 2. We hope to maintain throughout run 3, but also we believe we will be able, with upgrades of the trigger system, to also hold similar threshold. And you can see here a table of those main thresholds of trigger to hold this also at HL-LHC. Now, I just want to flash to you a few of the main achievements in terms of object reconstruction, and where I want to show you that reconstructing electrons, photons, and muons, and so not only reconstructing them stably as a function of pileup, but also also calibrating them with the data has been extremely important for all the analyses that we've carried out. And here I show you an example for the electrons and for the photons. We've done so also for jets, and for taus, where these are more complex objects, and in this case, the latest reconstruction algorithms make a lot of use of deep learning techniques, and this is making a large change in the performance that can be reached at the LHC. And I just want to flash to you as well the B and C jet tagging, which are extremely important algorithms for the Higgs physics, and I just wanted to show you how stable the B tagging is as a function of pileup. And finally, a plot that was shown by Fabiola at the symposium from ATLAS, just to show you the evolution as a function of time of the B tagging algorithms at a fixed B tagging efficiency of 70%. You can see here how the rejection of light jets has evolved from a factor of below 50 to a factor of above 1,000. So this is just to illustrate how impressive the improvement in performance of the reconstruction algorithms has been. Okay, so now let me move on to the Higgs discovery. And to start with, I just want to give you a flash to you just what were the conditions at the time. So, and what has been this evolution of sensitivity, in particular from the Aachen workshop, where for 100 inverse femtobarn, like 16 TeV was the condition that we thought we could see the Higgs boson, in particular here in the 4 leptons. At the ATLAS TDR in 1999, where we thought that we needed 30 inverse femtobarns and a K factor and a center of mass energy of 14 TeV to reach a sensitivity of above 5 sigma at 125 GeV. And here is the latest updates, take into account also all of the theoretical developments that occurred before 2009. So this was right before the start of the LHC. And you see that, in fact, the sensitivity told us that we could reach 5 sigma level at around 125. So between 115 and 150 GeV for 10 inverse femtobarns of data. So of course, we took data and we looked at the channels. And here I just want to flash to you the diphoton channel, where you have a beautiful signature here of 2 photons. So you see there's no track pointing to these 2 calorimeter objects, where some of the features which are most important in this case is really the rejection of the background. This has been what experiments have been struggling a lot through the years in the design of the detectors, but also of course an excellent calibration of the electromagnetic calorimeter to have the best possible resolution. And here I just wanted to show you how beautiful the peak of the Higgs to 2 photon is now with the full run-2 data set. And then you have the golden channel, of course. It was when you looked at the diphoton channel, you can see that the peak is right on top of a huge background. So very low signal to background ratio of approximately 1%. While in the case of the golden channel, the Higgs to 4 leptons, and you can see that we have a signal which is beautifully at a signal of a background much larger than 1. And there the challenge was always to try to not only to have an excellent resolution in the reconstruction of electrons and muons, but also to gain efficiency at very low PT, which was one of the limiting factors of the sensitivity. So you can see here that the trading lepton in PT is dominating the efficiency in this channel. And you have a beautiful 4-muon event from CMS here. And just to show you what the mass plot looked at the time of the discovery in 2012. So with 7 to 8 TeV and 25 inverse femtobarns of data, we reach a significance of 7 sigma. And this is about the significance that was thought that could be reached with 100 inverse femtobarns of data at 16 TeV. And so you see what 30 years of ingenuity and new ideas has brought to the field at the time of the discovery. And also I wanted to show you one beautiful 4-lepton event that shows you how high in S over B we can reach. And here we're just looking at 4 leptons plus jets, and plus jets in particular B jets. And this shows you how these events that are signature of the TTH production mode can reach extremely high purities and are very promising for the future in this channel. And finally, another discovery channel which played a very important role at the time of discovery is the Higgs to WW, which uses the feature of the scalar nature of the Higgs boson and the V-A nature of the W coupling to find signatures where 2 leptons, an electron and a muon in particular, are produced close together with missing transverse energy. And for instance, in the case of this event display, 2 jets in the forward region. And just to show you, of course, in this channel, having neutrinos in the final state, you don't have a good mass resolution. So it was absolutely key to have a good background model. And this showed us the huge progress that has occurred in the modeling of the backgrounds, but also, and this channel was critical for that, in how to probably define jet beam uncertainties. And this is the mass plot, the transverse mass plot as it was at run 1, and here is what it looks like now at run 2. Now, just a comment about the start of how textbook and timely the discovery has been. And just to show you that it took about a year. It came from, of course, a strongly motivated background and the significance increase really as expected from the luminosity increase. It was made by 2 experiments. It was a specific request from the CERN Director General that we do not combine the 2 experiments to make a discovery. It could have been done before otherwise, even almost at the time of 2011. And it had to be done in several channels independently. Now, let me get to a brief status of Higgs physics at LHC. And first mentioning that HL-LHC is a Higgs factor. It will produce about 160 million Higgs events. In comparison, the future E plus E minus Higgs factory would produce 1.3 million Higgs events. And of course, in this case, the events would be much cleaner and the effective precision that we would get out of it would be much better. I just wanted also to flash to you the evolution with the center of mass energy of a different cross-section to show you that also going to 13.6 TeV will still gain in cross-section, in particular for the channels such as TTH or HH, and we're very much looking forward to this. I'm flashing also the main production modes and the main decay modes with all the numbers that are needed, and you can see also the reference numbers of events produced at LHC. I'm not going to go through this in detail. Just to mention that when you look at the production modes versus the decay modes, you can see that at the end of run 2, all the channels, all the possible combinations of production and decay have been investigated. And this is the main result of the 2 Nature papers that have been published. So I've compiled the numbers in this table and try to walk you through it very briefly. So first, looking at the famous kappa measurements of the couplings of the Higgs to the W and the Z first, and these are now have reached a level of precision of 6%. And this can be translated in limits on, for instance, minimal composite Higgs scenarios of 90 eV on the compositeness scale. And this, of course, addresses the question of how elementary the Higgs boson is. And if you look at the couplings through loops, either through photons, gluons, or the Z gamma, where we have first results, this is probing new particles through loops. And you see that we've reached also the level of 6% precision in the 2 photons and in the gluon coupling, essentially. And then we also have results in 4 of the Yukawa couplings, the top, the bottom, the tau, and the muon, and with typical precisions of 10%, but of course for the muon, they're a bit lower, it's 20%. And this is probing the flavor hierarchy through the Yukawa couplings. So, and of course, we have projected these numbers at HL-LHC, and I've put in this column all the projected numbers, and you can see that precisions at HL-LHC reach 2% level for the main vector boson channels, and the 3 to 4% level for the main fermion channels. Now, another very important result was obtained by both experiments was limits on the invisible branching fraction, so the coupling of the Higgs boson to invisible particles such as dark matter particles, reaching a level of limits of almost 10%. And yeah, one important aspect about the projection is that the projections for the future are dominated by theoretical uncertainties on the signal, and they have been assumed to be about 1/2 of what they were at 1/2. And this is something that already now there's been a lot of progress since 2018 when these projections were made, and already a factor of 1.5 probably has been reached. I also wanted to flash just the measurements of the mass. This was the first precision measurement at LHC, which reached a level of a few per mil. And you can see the most precise measurement by CMS has reached the 1 per mil level. And the latest measurement from ATLAS, which is a bit less precise, which is only with the channel of the 4 leptons. However, it shows that we can reach a systematic uncertainty on the measurement of the level of 30 MeV, which means that we will be able to reach a much better precision eventually at the HL-LHC. Now, one important aspect that we've learned from knowing the mass of the Higgs is if we look at the precision measurements and the precision indirect measurements of the mass of the W boson, for instance, from precision electroweak measurements. And you can see here the indirect measurement of the mass of the W boson without knowing the mass of the Higgs boson. And you can see by knowing the mass of the Higgs boson, how this precision measurement is actually, this indirect measurement is actually much, much better and reaches a level of 7 MeV out of the mass of ATG, the W boson. And this is, of course, extremely interesting topical at the moment because it is in tension with the latest CDF measurements of that was shown recently. And just to mention that, of course, this also has an impact on the predicted top mass, and the knowledge of the Higgs mass has completely changed the picture for the electroweak precision indirect measurements. However, knowing it with higher precision than what we have would have no impact because the prediction is essentially dominated by theoretical uncertainties. Okay, so I see that I don't have that much time, but I wanted to go through at least some of the points here. So the essential role of theory predictions. So the dominant systematic uncertainty in most of the measurements and most of the analysis of HL-LHC are not experimental, but still dominated by modeling and theoretical systematic uncertainty. And this is changing. This is changing also because there are huge theoretical breakthroughs through higher order calculation, higher order Monte Carlos, higher order resummation calculations, and the improvement in the jet reconstruction algorithms, and also the pattern-shower and matrix element and pattern-shower machines. And this is undoubtedly a pillar of precision at the LHC. And this was another plot that was shown by Fadila at the symposium, and it showed, as a function of time since the early 80s, how the gluon fusion cross-section has evolved, and how now the prediction at N3 LO in QCD and LO in electroweak compares to the two measurements published in Nature by ATLAS and CMS. And you can see the very good agreement that has been reached, but you can see also the evolution of the calculation and how large the impact was on the cross-section. And this, of course, is an essential element of the evolution of the sensitivity as a function of time. Now, the fact that higher cross-sections were reached is, of course, because at next leading order, new channels are opening, and this has an impact not only on the total cross-section or inclusive cross-section, but also on the transverse momentum of the Higgs boson. And here I'm just showing a plot of several production processes and how the PT, the transverse momentum of the Higgs boson in these different production modes impacts, helps the discrimination of a typical background. In this case, in the diphoton channel, you have the background from two photons. And this has played an essential role, the use of the transverse momentum of the Higgs in the discovery as well. About 30% improvement in sensitivity was gained because of this, which means that the discovery would not have been done so fast if we didn't have all the hints from the calculations of higher order corrections for the PT. I also want to mention that now the state of the art in calculating processes at higher order with several patterns in the final state and several loops is key, and how much better we are now predicting the backgrounds in these analyses, and this will have an impact, a strong impact on the precision of these measurements, and this underscores really the importance of ancillary measurements. Also, boosting the Higgs boson has important implications if we look at analyses where the Higgs is boosted. And here I'm just reconstructing simply one jet, a large radius jet, and looking at its substructure that we can clearly see a signal from W and Z boson, where the Z boson decays to Bs and the W boson to CNS. And you can see this signal very clearly, but you can also see that we start to be sensitive also at the Higgs boson decaying to 2 big quarks here in purple. And this is shown by the significance in this search here that's reaching almost 1 sigma, and you see that there's also an excess observed in this channel. And this was thought to be completely impossible before we started taking data. And this has also an impact when we measure differential cross-section, which has, of course, is extremely important observable if we want to constrain a detector in new physics from higher transverse momentum data. And you can see that, for instance, the measurement of the Higgs to BB bar in this case is playing also an important role at high transverse momentum of the Higgs. Now, Roberto, how much time can I still have?
Time is over, but if you want, you can use maybe a couple of minutes to finish. Okay, so I wanted to mention early evidences, and I'll just flash them, and in particular emphasize that these evidence were not expected to be seen at the run 2 of the LHC. But you will see that they have been. So the first one is the Higgs to dimu1. Here you have a couple of nice event displays from CMS. And here you have mass spectra of a dimu1. And here you have the result. And you can see that both ATLAS and CMS start being sensitive and have first evidences of this signal. Another very interesting
measurement is the measurement and the observation of the decay of the Higgs boson to a gamma and gamma star, where a gamma star goes to a pair of leptons. So this is sort of an extension of, for instance, if you put dimuons, if you add a photon, then this would be an extension of this channel with the photon. And in this case, it's very important to be able to go at very low mass and very low mass of the two leptons. And just to illustrate that there's an analysis that has been done by ATLAS, where the two electrons are reconstructed very close together. And this has helped a lot in the sensitivity. And we see that the sensitivity was boosted up to being able to reach 2 sigma level and have an observation at the level of 3 sigma in this channel. Similarly, I just wanted to flash to you also the first observation of also first evidence, with an observed significance of close to 3 sigma in ATLAS and CMS for the search for the Higgs boson decay to Z gamma. And this is just to mention how the progress made in the reconstruction techniques and the quality of the data that was taken has really allowed us to do much more than we thought. And this, of course, leads us to how we can make the impossible possible. And here I just wanted to mention 3 examples. The first example is the Yukawa coupling of the Higgs to the charm, which was really thought to be completely impossible at the LHC. But using techniques, deep learning techniques, to really look into larger jets of Higgs bosons decaying to a pair of charged quarks, then things have improved really immensely. And this is illustrated by the CMS analysis that has shown very recently that they could reach limits with the run-to data at the level of 14 on the CMS strength, so on the rate of these events, and with the huge help of the analysis which is boosted. And you can see that this leads to constraint on the charm Yukawa coupling already at the level of 1 to 5. Now, if we look at the same channel projected at the high luminosity HL-LHC, this shows you that it reaches a sensitivity of almost 2 sigma for the CMS experiment alone. So this is extremely encouraging for the possibility of being sensitive to first evidence of the Higgs to charm at the LHC. Now, another very important example, and a very interesting example that stemmed from new ideas brought into the game, and this was in 2012, and there was an observation by Nicolas Kauer and Gian Piero Passarino, looking at the rate of events off shell, and realizing how important that contribution was, with a negative interference between gluon fusion and gluon to vector boson background processes. And from this opened the possibility to measurements of the Higgs boson, with just assuming that the running of the couplings of the Higgs to gluons and to gluons or top quarks and vector bosons were of standard model like, and taking a comparison with the on-shell measurements, putting limits on the width of the Higgs. And this was thought to be completely impossible before starting the LHC, measuring the width of the Higgs boson. And already now, with the run-2 data set, we have already limits or constraints which are below 100% on the width of the Higgs boson, and evidence of off-shell production, meaning that we have first evidence of a negative fluctuation of the rate of off-shell Higgs production at high mass at the level of 3.6 sigma. And with the HL-LHC, we would reach a level of 25 to 20% precision on these measurements. Now, I have to say that this projection has been done with analyses that were much lower sensitivity than the one that was produced here by CMS. And then the last point I wanted to make, and the last impossible channel that is becoming possible, and for sure, for all of you who were around in 2012, the first projection we had at HL-LHC for di-Higgs production were at the level of 1 sigma for each experiment. So meaning that there was no way that this was a physics case for HL-LHC. And this has evolved immensely. And here I'm just showing to you one event display of 4 B jets in the ATLAS detector. And just to show you the process of 2 Higgs production, both in the gluon fusion and the vector boson fusion production channels. This is an analysis that is extremely similar to the off-shell Higgs couplings, because we have to go and measure the Higgs production off-shell in terms of at least the trilinear coupling to be sensitive to the trilinear coupling. And it has an incredibly small cross-section, which is about 1,000 times smaller than the Higgs production, but still at HL-LHC, there will be more than 100,000 events that will be produced. And of course, we need to investigate all possible channels. And here you see the latest combined measurement produced in the Nature paper of CMS, showing that already now at run 2, we have limits at the level of 2.4 times the standard model observed in this mode. And combining all channels, so this is a note made by ATLAS. You can see that the constraints on the trilinear coupling are already at the level of minus 0.4 to 6.3, which are extremely strong with respect to what we thought would be possible before the start of the LHC. And looking at the VBF production mode, we are also sensitive to the kappa 2V couplings, so the VV-HH coupling. And I'm showing to you here just the limit obtained by CMS, which is already above 0, meaning that they're able to exclude at 6.6 standard deviation a kappa 2V of 0, meaning that the VV-HH coupling is measured already at the level of nearly 20%. So I will stop here on the discussion and go direct to my conclusion. So to celebrate the 10th anniversary of the Higgs boson, I think it's a perfect moment to just stop a little bit and reflect on what has been achieved since and where we're going from now. So what has been achieved? The machine experiments design, their construction, their commissioning, their calibration, the object reconstruction, the software, the computing grid, the analysis, as well as the theoretical predictions and the Monte Carlo simulations. All of these aspects have performed well beyond expectations. The progress was fueled really by a plethora of new ideas and pursuing really excellence in the operation and the detectors, and has allowed us to really hope well beyond what we thought would be possible. And I hope I've showed this to you through the last section of this talk. And the HL-LHC has really a superb Higgs physics program, and also well beyond the Higgs physics, of course. And the run 3, it's very important, I think, to keep in mind that the run 3 will provide excellent intermediate goals to push further what's going to be possible at the HL-LHC. And what about beyond the HL-LHC? I think the most important question for us is really what is the best machine that could be built after the LHC? And here I just want to paraphrase what Fabiola said at the symposium on Monday, and that if you look at all possible measurements, at least from the point of view of Higgs physics, there is no doubt that the FCC would provide the best possible constraints. And I want to close with the thoughts of Chris Leonid-Smith. After discussing the conditions for approval of the LHC, he discussed what he thought were the conditions for the approval of a major future project, and they are the following. First, a robust scientific case, which I think we have. Then major discoveries at the LHC, and this is from him that he believes that the Higgs discovery qualifies as a major discovery at the LHC, and I cannot disagree, of course. We need continued technical success. I hope that I've showed you that also this we can tick this point for sure. And a reasonable budget envelope and public support. So this clearly are more in question, but are things that we can at least work on. And of course, the unanimous support of the work particle physics community. And I just want to highlight this aspect, which is, I think, extremely important, is that at least among us, we can agree on what the best machine should be for the physics we want to do in the next decades. Thank you very much.
Thank you, Marumi. Thank you very much. We have time for maybe one or maybe two quick questions. So people can raise their hands.
There are questions in the chat.
Yeah, so we'll see. So if people want to ask, they can raise their hands.
Okay.
So there is one question from Harnath, please.
Can you hear me?
Yes, now we can, please.
Okay. Is there any possibility that there is a Higgs weak triplet rather than a doublet?
I think so. So for Higgs triplets, there is, of course, the possibility. You don't need to have. You don't need at all to have to modify the standard model for this. I think I'm reading now your question on the chart. The only thing is that if it's not doublets, then you might have to tune the VEV. But I think theorists can answer better than me on that one.
But your experiment is only interpretable with doublets.
Well, let's say that our experiment is showing one Higgs state. Okay, if we had a Higgs triplet, then there would be other states, and it is completely compatible with what is expected from a doublet, a weak doublet.
But your experiment has a specific weak isospin, so it can't be both.
Well, so you can have a triplet. So what do you mean by specific weak isospin? I mean, the way it interacts, it is completely compatible with a doublet, but doesn't mean that it doesn't come from a different representation, I think.
So this is John Ellis here. Could I?
Yeah, I think you could help me.
Please, John.
Try to join the discussion. So the ratio between the W mass and the Z mass depends quite sensitively on the isospin of the Higgs. And the specific ratio that's measured is compatible with a doublet, but not with a triplet. I mean, it could be a very small triplet contribution, but the dominant contribution must be a doublet. And also, we know what are the isospins of the left and right-handed fermions. And to connect them together with a Higgs to give a mass, we need an isospin 1/2 Higgs. So a Higgs triplet wouldn't do any good there either. I mean, there could be a Higgs triplet.
But the whole yeah.
There could be a Higgs triplet out there somewhere, but it's not playing an important role in the generation of the masses of either the fermions or the W and Z.
Right, but from the raw parameter, I see also a comment by Luis Alvarez-Garme. From the raw parameter point of view, as far as I understood, but if you tune the VEVs, you could have triplets, no?
Yeah, if the VEV is small enough.
Yes. So and so it's not ruled out. You could still have triplets, but it's not favored certainly by the data. Yeah.
It's not the dominant source of the mass.